Good day to all of you. We shall continue where we left off in the last class with our objective of trying to design a controller for a switched mode DC-DC converter. As you recall, we had spent considerable amount of time in modeling the DC-DC converter, and we have arrived at the state equation model. I am not going to write the state equation model, I am just going to indicate in the form of a picture the plant model. We have the plant, which is the DC-DC converter. It could be any DC-DC converter, and this converter is having a power input, which is Vg. It is having a power output where we have V naught. It has one control input. The control input is D, duty ratio. It has a output to be controlled Y, that we call, which is sensed and taken from the power output V naught. Okay. And here on the signal control side, we have a comparator which compares a reference desired value of V naught with the actual measured value of V naught, and this compared value, the error, is given to a controller. This is the controller, and the output of the controller, which is called the control voltage Vc, voltage to duty ratio converter, V to D or V to time conversion block, that is this, and the duty ratio in the form of pulses would actually reach the switches of the converter. We shall of course look in detail on the actual circuit diagram and how the duty ratio is affecting the switches by means of a simulation later on, but for now today we are looking at how we are going to design this crucial block called the controller block. And the last class we also spent some time in discussing this relationship between the error and the control voltage Vc, and we call that known as the controller gain K. Now, this control gain K we saw is needed to be very high, a value which tends to infinity, to a very high value. So, if this is very high, the result of this is that the error tends to 0, because we saw that the error is nothing but Vc by K. So, if K becomes high, tends high, E tends to a low value. However, we saw that we had two problems in the last class. Problem 1, noise. Noise is the issue, and especially if you have the controller gain K as a very high value, then noise which is generated in every component in the electronic circuit will also get amplified by this infinite gain, and it will swamp out all useful signal. So, you will only have noise at the inputs and the outputs. The second problem was that of limited input to the system. That is the power supply which is given to the signal conditioning circuits of the switched mode converter, DC-DC converter, is generally plus minus 12 volts or plus minus 15 volts, 0 to 5 volts, 0 to 3.3 volts and so on. And these put a limit on the input absolute input voltage value. And therefore, as a consequence, you cannot give any value from minus infinity to plus infinity. An error, if it swings beyond a particular value, it will saturate the input. It will go and get stuck to either a plus 12 or a minus 12 voltage limit. And once it gets saturated, there is no longer closed loop action, and as a result, the system will be in open loop, and our primary objective of closing the loop is not met. So, therefore, these two are very important issues that needs to be addressed, okay, and that is what we would do in the remaining portion of this class. So, therefore, we cannot, even though practically it is possible to set k, even though it is possible to set k to a very high value. See, we have op-amp comparators. The op-amp comparators with power supply given as VCC VSS, again limited plus minus 12 volts. This is the output of the op-amp. And let us say we set it at VC, and we have the error E. Now, this op-amps have gains of the order of 10 to the power of 8 and excess of that. So, you can go to really high gains. So, component wise, technology wise, we do have capability to give very high gains and position them in the system as controllers. However, because of the previous two problems that we mentioned, noise and limited input, we can't do that. So, therefore, k setting to infinity is not allowed. Now, this would imply that E cannot be equal to 0. So, this as a consequence of this decision. So, if we cannot have k set to infinity, E cannot be 0 under all conditions. So, therefore, we need to make a compromise. Let k be set to infinity under some conditions, and that is under steady state conditions. So, under steady state conditions, can we set k to infinity, which means that under steady state conditions, if we are able to set k to infinity, E which is equal to any control voltage by k will get set to 0. So, steady state accuracy is achieved. However, during dynamics, we relax this condition. K is not equal to an infinite value during dynamics or transients. So, let us do a k which varies with frequency. In such a way that at DC or steady state, k will be set to infinity. During at transients or high frequencies, k will tend towards a low value. So, let us shape the k in such a manner, make it a variable k, such that it follows these kind of constraints. So, under such a condition, you can say during steady state error will be 0 and during transients error is not equal to 0, and this in fact is what will try to solve the two problems that we mentioned, that is the noise problem and the issue of limited input. So, let us just look at a graph, get a picture of what would happen if we look with respect to omega, which is the frequency, in radians per second. So, if you have frequency in hertz, omega would be 2 pi f radians per second. Okay. So, on the x axis, let us have omega frequency, and on the y axis, let us have two components. One is of course the gain, and another thing would be the noise sensitivity or the noise amplitude. Let us just put it plain and simple, noise amplitude. So, this noise is not so significant in the low frequency. So, it is low at the low frequency, gradually starts to increase towards the high frequency portions of the system. So, if you demarcate so this region is the LF or the low frequency region, and this region towards the right is the HF or the high frequency region. So, in most of the systems and especially in the DC-DC converters which are switched, you will see that the noise is more predominant in the high frequency zone. This is the high frequency zone. It becomes very significant here, and not so much in the low frequency zone. It is more, it can be tolerated much better, and therefore, you need to address this portion of the gain that is seen by the system. Now, if you look at the gain, so let us say that the gain here is an infinite value. Imagine that the scale is pretty large vertical, has an infinite value there. Now, let us say our initial proposal was to have the gain value k constant at a very, very large value. So, this is k set to a very large value, infinite value. Now, what would happen? K not only amplifies the signal, it also amplifies the noise part, which is inherent in the circuits being generated within the components, and these noise components, noise parts of various frequency get amplified by infinity and swamp out any meaningful signal. So, therefore, what is required is that we need the gain, let us say this is 0, we need the gain to take a turn somewhere here, let the gain take a turn somewhere here, start falling down and maybe even going to 0, at high frequencies. So, this is what we need our new gain to look like. It is high, it is having a high value in the low frequency region, the low frequency region a high gain, at DC especially it is a high gain, and as it starts, as the frequency starts increasing, we want the gain value to fall such that it in fact attenuates the noise at the higher frequency. So, that is basically the principle, and we want to shape the gain curve in this manner, this being the noise, and we want to attenuate the noise which are predominant in the high frequency region. So, the next step is to make an implementable gain, a gain that has a large value at DC and a very low value as omega becomes higher and higher. So, let us slightly change the notations. So, let us draw this kind of a curve. Now, let me write here Vc by E. Now, this is the gain k. Okay. Now, let us say this gain k, we are going to replace it. This symbol we will replace it, because k is normally represented for a constant. This is being replaced by G C, gain of the controller. So, the G C means gain of the controller, which can vary with frequency. Now, this is a function of omega. This is no longer a constant, it is a function of omega. Now, we are talking of infinite gain to 0 value of gain. So, you will see that the vertical axis is pretty expanded, elongated. So, let us compress the vertical axis. So, a good means of compression would be to take the logarithm, log to, let us say, base 10, okay, and let me push this, log to base 10, you have Vc by. So, this will compress the log, the vertical axis gain, and if you want to express it in dB, 20 times this log is a dB value. So, we shall say 20 log, 20 into log. Now, this means that the gain, this is called the gain, which is expressed in dB, decibels. Okay. So, this is done in order to compress the vertical scale, so that you can put it in a reasonable framework within a page. So, this is being expressed as dB. So, always remember that it is nothing but 20 log to base 10. So, just to give an idea, if the gain, let us say you have a gain of 10, sorry, let me write it here. Let us say we have 10 dB. So, now here this 10 dB is actually coming as 20 log base 10 Vc by Ve. What is this ratio? What is this ratio? So, Vc by E is nothing but 10 by 20, 0.5, 10 to the power of. So, 10 to the power of 10 by 20. So, this is nothing but root of 10. So, if Vc by E is equal to 1, okay, the absolute gain, the actual gain is 1, then in dB wise it is 20 log base 10 1, which is 0 dB. So, this is 0 dB there. So, when you say 0 dB, it implies unity gain, absolute wise unity gain. So, keep that in mind. So, let us say So, let us say that we have an integrator, just to give an idea. Let us say we have an integrator. The integrator has an input and an output. So, in the Laplace domain, this integrator is written as 1 by s. Now, s is the real part is 0. So, s is j omega, it is actually 1 by omega. Okay. So, as omega increases, this gain keeps decreasing. As omega increases, Gc decreases. So, at DC, when omega is equal to 0, the gain is a very high value, infinite value, and at very large frequencies, very high frequencies, the denominator j omega is very large, and therefore, the gain seen by the gain presented by the controller is very low. So, essentially you will see, if you take it in logarithmic scale, you will see a straight line which starts going down like this, and it starts going down at the rate of 20 minus 20 dB for every 10 times change in omega, because you have now the gain as 1 by omega log to base 10, 20 is the gain in dB, which is nothing but minus 20, which is nothing but 20 log base 10 1 minus 20 log base 10 omega. Now, this portion is 0. So, you can remove that. So, you are left with only this. So, let us say this results in some dB. So, what is the absolute value of omega? Omega would be dB by 20 minus this 10 to the power of. So, now let us look at this itself. Let us look at this 20 log base 10 omega, which is the dB gain. Okay. Now, omega is equal to 1, then the dB gain is equal to 0. Omega is equal to 10, then log base 10 is 1. So, then the dB gain is minus 20 dB. Omega is equal to 100. Log base 10 100 is 2. 2 into 20 40 minus 40 dB. So, the dB gain becomes minus 40. omega is equal to 1000. Log to base 10,000 is 3 into 20 minus 60. So, dB gain is equal to minus 60 and so on. 10 kilohertz. You see that the dB gain is equal to minus 80. Omega is equal to 100 kilohertz. dB gain is equal to minus 100 dB, so on. So, you see here, for every 10 times, this is a decade. Between 1 to 10, you are multiplying by 10, it is a decade. This is another decade. Another multiplication by 10. For every multiplication by 10, you have a decade, we will call it as a decade. For every decade increase in omega, there is a 20 dB decrease, minus 20 dB. So, you will say this is 20 dB per decade. This is another minus 20 dB per decade, so on. So, you will see that you will have a linear curve like this, what we see at minus 20 dB for every 10 times change in frequency or 20 dB per decade. Okay. So, that is the character of the integrator. This is nothing but the integrator. This is nothing but an integrator. The integrator seems to give a gain curve something like this. If GC is the gain curve of the integrator, so this is how the gain curve will look like. This is a straight line. Imagine that it is a straight line, even though I have not drawn it strictly straight. And it falls at minus 20 dB for every decade, every 10 times change in omega. So, this is a very nice block. This is a very nice component that you can use, which has a natural gain pattern like this. Very high infinite gain at DC, this is DC towards DC, and a very low gain towards higher frequencies. As the frequency is increasing, the gain starts falling down. Okay. So, this pattern, this component will be our basic building block in the controller, and we will use it extensively to design controllers because of this natural falling gain pattern, which actually is very close to the desirable thing, where we want the gain to be infinite in the low frequency region and start going low towards the high frequency region. Okay. It may not follow exactly the same kind of a pattern as we have shown here, but nonetheless, you have infinite gain in the low frequency region and very low gains at the high frequency region. You should observe that this point 0 dB is absolute terms wise unity gain. So, this 0 line is nothing but unity gain. Above that, above this is amplification. and below that would be attenuation. So, minus dBs, minus 1 dB, 2 dB, 3 dB would imply attenuation. So, any point at any of these points, gain points, would imply that the output is going to be attenuated with respect to the input. Okay. So, proceeding from here, this is one component. Let us take another component and see how it looks like with respect to omega, and then we will try to integrate these various components to form one integrated controller. So, let us look at the gain in dB. We have at this point 0 dB or unity gain. Now, let us consider a block which is a constant, just a simple constant k. You have the input and the output. We will say the input is E, output is V c, because in this case the input is the error and the output is the control voltage. Now, if this were the case, the gain G c is equal to k, is equal to 20 log base 10 k gain. Now, if k were a constant, then k is independent of frequency. So, 20 log base 10 k is a constant value. So, you will see that it will take on a curve which is something like this. (20 log base 10 k) in dB. If this was amplification, or if you are having k which is less than 1, for k greater than 1, so it can vary anywhere here, or it could be here 20 log base 10 k. For k less than 1, you will have variations from here to here. So, this is attenuation and this is amplification. And as k is constant, 20 log base 10 k will be constant and it will be a constant value throughout. Okay. So, here you say that the output, controller output is proportional to the error input. Okay. So, this is a proportional component. This is a proportional component. We saw earlier 1 by s, nothing but an integral or integrator component. Here just a constant k is a proportional component, and the proportional component gives a variation of the gain with respect to frequency, which is like this, and this is nothing but a constant, as k is independent of frequency, unlike the integrator which gave a k which was falling with respect to frequency. Now, let us look at one more important component, which wherein let us say for example that gain in dB and this point is 0 dB. So, let us say that we have gain pattern going like that 0 dB, and at some point here it starts taking a turn like this. Now, this is interesting in the sense that up to this point you do not have neither attenuation or amplification, it is unity gain, and from here on you are having amplification. Now, let us say, can we obtain an amplification at the rate of plus 20 dB per decade, just like we had minus 20 dB per decade for the integrator. So, how do you get plus 20 dB per decade? Let us reframe this problem. In the following manner, let us make it simpler by saying that like the integrator, let this also start going like this from 0, and from 0 it is going at plus 20 dB per decade. So, you see that it keeps on going towards infinity. Is such a thing possible? Now, to get this, it would mean you need to have 20 log base 10 omega. So, here omega is equal to 1, then dB gain will be 0, omega equals 10, dB gain will be 20 plus 20 dB, omega is equal to 100, dB gain will be plus 40, so on. So, you see that for every decade you have plus 20 dB per decade, 20 dB per decade. So, to get 20 dB per decade kind of a situation, you need to have a gain, a controller gain, which is like this, just omega multiplied by omega. Which component will give you such a gain? Which component this implies that the component omega should be your controller gain. So, just like we had 1 by s, which is nothing but 1 by omega, because the real part of the integrator is 0, you have in the s plane the integrator pole located at this point. So, the movement along the j omega axis. Likewise, to get omega, which would imply S or a derivative. So, the transfer function here would mean it is just S. But remember, you cannot have a pure derivative. This in this form is not implementable. A pure derivative cannot be implemented because we cannot know the future. It is a prediction. What does it mean? Derivative is nothing but the slope. So, let us say you have a particular evolution of a particular signal, and you are seeing things with respect to time, and let us say at this point this is now. So, what do we say the derivative at now? Nothing but you take a small deviation from that operating point, another small deviation from that operating point, and you will say that now this is, let us say y, this is t, let us say delta y, and this is delta t, because in this case it is t as the x axis variable. So, the derivative is delta y by delta t in the limit as delta t tends to 0. Now, this is now, this point is the now point, and this point is the future point, and this point is the past point. So, you can always get the past point, you can measure it, you can get points up to the now. Beyond that future you cannot get, it is only a guess. So, you can never always get any of the points after now. So, therefore, you can never truly get dy by dt. You can at most get this triangle, but this would mean the derivative of this, a point which is just before now. So, it is actually the derivative of the past or delayed derivative. Okay. So, you cannot get S, you can always get a delayed S, and that is, the delay is nothing but a low pass filter. So, this is a low pass filter, this is the derivative at now, but derivative at now you can never get, because you cannot measure points greater than this, later than this. So, you have these 2 points, and therefore, the derivative which will represent the derivative of the point in between, and this is actually in the past already. So, it is lagging by some time, and that lag is represented by this low pass filter or the lag effect. Okay. So, always an implemented derivative is of this nature, S by S plus A. So, therefore, what is implementable is something like this. So, let us see how the gain looks like for this. So, this is the gain in dB, and this is with respect to the frequency. This point is the 0 dB point. So, this is Gc, which is a function of omega. Now, let us replace Ss by omega. So, let us say Gc is 20 log to base 10 omega by omega plus A. So, how this would turn out? This would be equal to 20 log base 10 omega minus 20 log base 10 omega plus A. So, look at this. This is like your pure derivative, like the S term, the d by dt term, d by dt. Now, this is another term which is the lag effect, which is bringing in the lag effect. So, let us say at omega much lesser than A, this portion is a constant, okay, or if you say we shall say omega can be taken out and we will rewrite it in this form, omega 1 plus A by omega. So, case 1, when omega is small, when omega is small, this value is higher, okay. This particular expression would lead to something like this. So, let us say it goes in this manner. There is no space. Let us take a fresh page. Let me quickly put this versus omega. Take first just 1 by omega plus A. So, 1 by omega plus A would give, so it will be at omega equal to 0, it will just be going along, just be 1 by A, not along 0, it will be just giving some again. Let us say it A up to some omega equal to a, and then further on it goes like that. This is minus 20 dB per decade, that is at omega much greater than a, the lag portion becomes 1 by omega. A is neglected. At omega much lesser than a, you can just write it as 1 by a. So, it could be an attenuation or gain depending upon the way depending upon the value of a. Omega can be neglected, it is constant. So, you have a constant and then you start having a drop minus 20 dB per decade. Of course, it would in actual practice it would be a smooth curve like that. Now, the derivative portion starts giving a value which is increasing at plus 20 dB per decade. So, that portion gives you an increasing curve at plus 20 dB per decade, 20 dB per decade, and this lag portion gives a minus 20 dB per decade at high omegas. So, therefore, we land up with, you will see that at this point there is a cancellation, a plus 20 dB per decade, minus 20 dB per decade, beyond a there is cancellation, up to a there is a build up. Okay. So, which would mean that it starts building up like this, then beyond that plus 20 dB per decade and minus 20 dB per decade cancels and there is no further increase, it keeps going like this. So, this would be the nature of the derivative that can be built up, that is S by S plus A kind of a block. So, this is called the derivative block. Derivative block. So, you have an integrator block wherein the gain in dB starts falling like that. You have a proportional block where it is constant with respect to frequency, and you have a derivative block where it increases and then stays flat with respect to frequency. So, this is the I block, this is the proportional block, this is the derivative block. Now, these three blocks we will try to combine them in the next class and build an integrated controller. Thank you.